Okay, so hello everyone and welcome. I'm Maksymilian Jaworski. I'm a data engineer at STX Next. And today I would like to talk about, show you some common data engineering problems and how we are trying to solve them with Python. But firstly, let's try to answer the question, what exactly is data engineering? Because I hear this question quite a lot. And while preparing this presentation in the internet, I found many different quotes and statements about it, like that one, that data engineering is the practice designing and building systems for collecting, storing, and analyzing data at scale, with application in almost every industry. Or another one, that since data is all around us and is growing every day, software engineering has evolved to include data engineering as a sub-discipline that focuses directly on transportation, transformation, and storage of data. Or something slightly simpler, that data engineering is the foundation for a successful data-driven company. But I'm afraid that this quote don't explain everything to you. So let's try to answer another question. Who are data engineers, or rather, what are they responsible for? So data engineers are the people who are responsible for making raw data usable for data scientists, business analysts, and all other groups within an organization for further data-driven work. This data-driven work can include training machine learning models, doing some data analysis, populating fields in application with outside data, and many, many more. So in a nutshell, we could say that business intelligence, data science, or any other data-related teams are the customers of data engineering teams. It could be demonstrated with the picture created by Terence Shin, that the same way we have physical needs like food and water before social needs, for example, relationship, companies should satisfy a few requirements which in general fall under the data engineering umbrella. And as we can see, data science, and especially machine learning and deep learning, should be the last thing to satisfy, so to speak. I'm not saying that those things don't matter. I'm simply telling you that there can be no data science without data engineering. Or at least that's what the theory says, and that's why probably Terence Shin wrote, as I quoted before, that data engineering is the foundation for a successful data-driven company. Now, I know that probably some of you may not agree with this picture because there is a lot of data scientists who are also doing plenty of data engineering tasks, and there are data engineers who are doing machine learning, but just let it go, it's just a picture. Okay, so once we have a bigger picture of what data engineering is about, let's go into some details. What are typical data engineering tasks, or fields of action, so to speak? What are those data pipelines that you often hear about consist of? So first of all, we've got data ingestion, and I added here storage as well, because the main point is that data engineers have to somehow connect to various storage types and extract data from it. Difficulties here, well, data may come in different file formats, like comma or tab separated files. There could be JSON files, there could be column-oriented formats like Parquet or org files, and so on. Also, often we have to deal with both structured and unstructured data. And what's more, this data may lie in various SQL and NoSQL databases. In data lakes, we might need to scrape data from websites, get it from streaming services, from APIs, and so on. Secondly, we've got data transformation. So data need to be adjusted somehow to some kind of architectural standard. We've got data normalization and cleaning here, so the processes that make the data more accessible to users. This includes tasks like changing or eliminating garbage, incorrect, duplicated, somehow corrupted or incomplete data in the dataset, casting the same data to a single type, ensuring dates are in the same format, etc. We also perform some less or more complex aggregations, and since all these transformations are often performed on extremely large amount of data, like hundreds of gigabytes or terabytes, there is a obvious need for a parallel computing. Next thing is data orchestration. Well, since data pipelines consist of many elements, many data sources, many transformations, many data sinks or targets, so to speak. We are not writing them as a single large block of code. They are built from separate, relatively small pieces, which often use various kinds of technologies or clouds. We need to somehow connect these pieces, schedule the whole process. Sometimes we need to make some decision based on incoming data, maybe replay part of the pipeline, or we need to apply parallelization for some part of the process. And for all these tasks, believe me, we need some bigger tools than a cron tab. So that's the orchestration part. And finally, I'm not sure if we can call it a task, but modern data engineering is often done in the cloud. So we need proper tools to efficiently work with these clouds. And of course, we could mention many other tasks and responsibilities, but let's briefly focus on these four during this presentation. So what kind of Python libraries and Python-based tools are we using? Let's start with data ingestion and storage. We know that there are plenty of different databases, so how to connect to them? And here comes SQL Alchemy. It is probably the most commonly or widely used library. It is an object relational model library, and it currently supports, let me check, MySQL, MariaDB, PostgreSQL, Microsoft SQL Server, Oracle DB, and SQLite. And it consists of two distinct components known as the core and the ORM. The core is a fully featured SQL toolkit, which allows us to interact with a wide range of database APIs. In Object Relational Mapper, we can map classes to the database schema, and this ORM is optional, but to be honest, that's probably the main reason why SQL Alchemy is so popular. And there are other connectors like MySQL connector for Python, PyODBC, which is recommended for Microsoft Server, PyMongo for MongoDB, Redis Py for Redis, and many others. Basically, every known database or data warehouse, you name it, Elasticsearch, Snowflake, etc., probably has its own Python connector, or at least recommends using some generic one, like in the case with Microsoft SQL Server. For websites and APIs, we've got well-known request library, and it's often used in conjunction with Beautiful Soup. We've also got Scrappy. Scrappy allows people to write small amounts of Python code to create so-called Spider, I believe. Spider is an automated bot which can go through web pages, scrap data from them, so we can download, clean, and save data from the web. Beautiful Soup, on the other hand, is helpful utility that allows us to get specific elements out of a web page rather than scrap the whole web page, like the list of images, for example. So let's go to the examples, because presentations without examples are probably boring. Let's start with MySQL database. How to query MySQL database with MySQL connector. Well, I hope that you can see it clearly. It's just a few quick steps. We create a connection, and in order to put our new connection to good use, we need to create a cursor object on top of this connection, and basically we are good to go. We can write a query, execute it with a cursor, and fetch all the results. How to work with MongoDB? Also simple, create client connection, set database, set collection, and we can insert some sales representative, for example. And in the last part, we are trying to find one by name and print it out. What about, let's say, Redis? Still pretty simple, pretty similar. We create a connection, set some value, get this value by key, right, byte key, get this value back, searching by key, and print out. So as we can see, it is very simple, just a few lines of code. However, I would like to make a note here. Please remember that these are just examples, and storing your credentials inside your code is a very bad practice. You should always use config files. And of course, in more serious projects, we would use things like exceptions, etc. But here you get the main idea. The main point is that it takes just a few lines of code to start working with almost all databases. Next to the beautiful soup, and here let's take a look at the example from the official documentation. We've got an HTML document that's part of Alice in Wonderland story. So in the second line, we are using HTML parser to get beautiful soup object, which represents the document as a nested data structure, and that's basically all. We are good to go. We can now use title function to get the title, and we can use title.string to get just the string, or find all to get all the tags and strings that match our filters. What else can we do with beautiful soup? We can easily extract all the text from the page, and we can do many more things. We can even modify tags, replace them, insert new ones, etc. And why I said before that we often use beautiful soup on top of requests library? Well, because often we have to get those HTML files from the internet first. So in most cases, it looks like this. First, we create the request and get the data, then load to beautiful soup, and we are good to go. Still pretty simple. Our next issue is dealing with various file formats, and here comes pandas, which allows us to interact with almost every known file format. For some of these, we only have reader functions like org or SAS, and for LaTeX, I believe we've only got a writer, but in general, we can work with almost any file format. And I'm pretty sure that if something is not directly supported by pandas, there is some workaround solution how to read this data to pandas data frames anyway. And apart from various file formats, we also have streaming services, with Kafka probably being the most popular one. So to work with Kafka, we've got, at least I'm aware of, 3 Python libraries. However, I think that the first one should be the best since it's created by the Confluent, so people who originally developed Kafka. PyKafka, for instance, is not supported since 2018 or 19, I believe, but it can be seen in a lot of examples and articles. And for other streaming services, like for example Amazon Kinesis, we've also got dedicated Python libraries. So back to the examples, how to read and write from these various sources, various data types that I've just mentioned. For example, to read a tab-separated file, we can use read_CSV function and just set up a tab as a separator. To read Excel file, we can use read_Excel function. And in this example, I'm only interested in the first sheet, and I want to convert a date column from \separated to --separated. So I added additional 2 parameters to the function. So as you can see, these are basically one-liners, nothing fancy. And next example, how to use pandas in combination of requests. Well, it could look like this. We create a request to the particular URL, then we take JSON object of the result that we've just received into data variable in this example. And with pandas function JSON normalize, we convert this semi-structured JSON, basically data into a flat table. And in addition, here I was only interested in domains part of the JSON. And for the sake of brevity, in the last line, I selected only four columns to print. What about PDF files? Well, we can use, not mentioned before, Tabula package to read tables directly from PDF files. And as you can hopefully see on the left side, there is a part of PDF document which has some tables. And with Tabula, it takes just 3 lines of code to get these tables. Isn't that nice? I didn't even know this library until I started doing this presentation. So, but by the way, Tabula also allows us to convert a PDF file into a CSV and a TSV and a JSON file. So it has more features. Next, as I said before, data cleaning is the process of changing or eliminating or fixing incorrect, duplicated, somehow corrupted or incomplete data in a dataset. So how do we handle this? Well, we can once again use pandas, and I've shown you before how to access data with pandas. Now let's take a look at the data manipulation functions. And for my next tricks, I've imported the following table, where we can have some general info about some customers, like first name, gender or country, and some additional information like mysterious date or a column named param. So let's start with missing values. How to find missing values? We can use isNA or isNull to find it, but in this format, it's pretty hard to immediately see all the missing values. So let's maybe try something like this. We can add any function at the end, and it looks slightly better. But let's say that I want to know how many missing values we've got for particular columns. Then I can simply use sum instead of any function, and we've got something like this. Pretty clear, pretty simple. And what about how to fill missing values? Well, we can use fill NA function, and we can see that for all missing names now we've got a dash, and missing age is filled with 0. So we could also drop rows with at least one or all none values with function drop NA and so on. There's plenty of options how to handle missing values. And with pandas, we can solve pretty much all previously mentioned problems. And some solutions may be really simple, like finding or removing duplicate values. Here we've got some examples. On the left, I'm just checking for duplicates. And in this example, I'm not looking at entire row as a duplicate, but I'm deciding that the row is duplicated if column ID was duplicated, as you can see. And on the right, you can see how to drop duplicated rows, keeping the first one untouched, right? So we can see that row with value 11 in column param was dropped here. But some things may not be so obvious to do, like finding outliers in our dataset, for instance. So in statistics, an outlier is an observation point that is distant from other observations. Often we assume that value is an outlier when it's more than 3, 4, or 5 standard deviations from the mean. There are many other ways to define outlier, but let's just keep with this one in this example. Now let's say that we want to look for outliers in our meaningless param column. How can we do that? Well, writing something like this. We calculate upper and lower boundaries, and just filter out our data frame based on column param. And as we can see, the row number 7 is missing, as it had value 387 in the column param. So Pandas is not providing functions for all data cleaning functions, but it's still pretty simple to apply any mathematical logic to the data frames. Okay, what other transformations do we do with the data? Well, we perform various counts, sums, averages, we join data, apply conditioning, we use window functions, and many more. Now, of course, Pandas can do this as well, but let's move to something bigger, Apache Spark. Apache Spark is an extremely powerful and fast analytic engine for big data and machine learning. We'll come later to the part why is it so powerful. Let's now focus how to do some basic calculations and joins. We'll use a CSV file which apparently contains data about some invoices. We've got some customers, items description, quantity, unit price, etc. And by the way, as you can see, accessing CSV file in Spark is also very simple. It looks pretty similar to the previously shown Pandas code, so it's also nice. And I should probably mention that Spark supports 4 languages. You can use Java, Scala, Python, and R. But since it is a Python conference, it shouldn't be a surprise that I used PySpark for my next examples. So what can we do with that data? Let's start with some simple count. Let's just count number of records and group by customer. It would look like this. Pretty simple, right? We just group by column customer ID, do count, do descending order by the count, and print first 5 results. But as we can hopefully see in the first row, the biggest count is for customers null. Now, I would like to remove that, and I would also like to do some more meaningful aggregations. So let's take a look at this example. So here I first filter out null values, then I group by a customer, and I perform 3 aggregations. I sum the multiplies of quantity and unit price, round this value to 2 decimal places, and I want to know distinct number of purchased items and total quantity. Also, I gave each calculation a proper alias. And what's more, in the last part, I'm only interested in customers who purchased more than 50,000 items. And I ordered that dataset by total items value and print first 5 rows. And here we've got results. So still something maybe not very simple, but certainly not very complex in my opinion. We just apply one transformation after another. And in my opinion, it looks pretty similar to SQL queries. So if someone is familiar with SQL, it shouldn't be a problem for him to learn Spark data frames, how to work with Spark data frames. And what about joining data frames? Here I am saving the results. So the first part is the same as on the previous slide, but I'm saving it to the separate data frame at the beginning. Then I load some tab separated file to data frame called customers, and I perform a join on the column customer ID from one data frame and ID from another one, so the customers one. I select 4 columns: name, surname, total items value, and totals item count, order by totals items value, and print first 5 rows. Results done. That's all. Still pretty simple. So that leads me to last thing about data transformation: parallel processing. And here we've got Spark, which is designed to process data in distributed way. And that's why, amongst many other features like lazy evaluation or caching intermediate results in memory, that's the reason why it's so powerful. Now, I wouldn't like to go into details because the whole presentation could be only about Spark, and it probably won't be enough. But please keep in mind that if you're processing or transforming millions or billions rows at once, Spark with a proper infrastructure is probably the best tool to do it. But anyway, we also have Dask, which in contrast to Apache Spark is a pure Python framework and does not even aim to be a complete ecosystem. And Dask was built because libraries like NumPy or Pandas were not originally designed to scale beyond single CPU or to work with a data that does not fit into memory. And Dask allows us to easily run the same Pandas or NumPy code in parallel, either locally or on a cluster of machines. And if we are talking about parallel processing strictly on one machine, there is a threading option and multiprocessing option in Python. Now, threads can do things in parallel, but can't do things concurrently. So they can go back and forth between tasks. So they are good for IO-bound tasks. When we are waiting, for example, for input or output operations to be completed. So, for example, we are downloading stuff online or waiting for API response. And multiprocessing is designed to do things in parallel, so they are extremely handy when we've got CPU-bound tasks, like doing aggregations on, millions of rows or processing hundreds of images. And that's all about data transformation. And now let's move to data orchestration. And first of all, why we even need data orchestration tools. So we may have a pipeline of tasks that needs to be run once a day or once a week. These tasks maybe need to run in specific order, like this. So the first be A, then B, then C, last D. but they may grow and become more of a network of tasks with dynamic branches and so on. And we call these things DAGs, so directed acyclic graph, because data in DAGs should only flow in one direction, or in other words, it has no cycles. So not only we need to organize tasks into DAGs and schedule them, we also often want to be able to monitor them easily, dynamically parallel some tasks, maybe wait for a file to appear before we start processing it. Maybe you want to use some common or shared variables, and maybe in case of failure, we would like to replay DAG starting from particular task, like C in the middle, not from the beginning. So that's why we need orchestration tools, not just a cron tab. So what Python-based tools do we have here? Well, we've got Apache Airflow and Daxter. We've got Luigi, Prefect, Kubeflow, MLflow, and many other solutions like Mara or Kedro. In overall, I would say that Airflow is probably both the most popular and also has probably the broadest range of features. Luigi, designed by Spotify, is a similar tool that's probably simpler to get started with, but it's lacking some of Airflow features. For example, Airflow can run multiple DAGs at once and can trigger a workflow at specified intervals or times. Also, it is way simpler in Airflow to build more complex pipelines, where we, for example, want one task to begin before the previous has completely finished, for example. Prefect could be compared to Luigi, as they both aim to be lighter and simpler than Airflow. Because in Airflow, for example, we are using Python, of course, but we have to define tasks in a specific way. While in Prefect, any Python function can simply become a task. And one last thing about this, that Prefect is open source, open core, while Luigi and Airflow are both open source. Now, going back to big guys, Daxter is another pretty new tool which can be an alternative for Airflow or basically any other workflow engine, because it can schedule, order, and monitor our computations. And judging by its features, I think that only Daxter could be really compared to Airflow, to be honest. And Kubeflow and MLflow, they serve more niche requirements, and they are rather related to deploying machine learning models and tracking experiments. So they're designed for ML rather. And last but not least, cloud. How can we use Python in the cloud? And as my team colleague wrote in one of his articles, I quote, "Python has proven itself to be good enough to encourage cloud platform providers to use it for implementing and controlling their services." So let's take a closer look. As we all probably know, we've got three main cloud providers: AWS, Google Cloud Platform, and Microsoft Azure. So let's start with computing services. What about serverless computing services? Now, all three providers have services called functions. In AWS, it's a Lambda function, GCP has Cloud Function, Azure has Azure Functions, and all of them support Python language. So basically, we can run in the cloud almost any Python code we want. How it is useful? What are the examples? Where, for instance, with AWS Lambda function, we can trigger Apache Airflow DAGs once some particular file is added to S3 bucket. Or we can simply run some image resizing code once photo is uploaded into a S3 bucket and save it back to S3, maybe even save some metadata about this event into RDS, so relational database system of AWS. So plenty of options once we can apply Python code in the cloud. So next question, can we use Apache Spark in the cloud? And the answer is yes, we can. All three providers provide us with services designed to run and manage big data frameworks, and all of them include Spark. So that's checked. What if you want to write some custom code? maybe to create, manage, and work with cloud services. Well, AWS has got both a free library. With GCP and Azure, things get a little more complicated, as they both have separate libraries for separate services. So, for instance, in order to, in Google Cloud Platform, we need to install separate package to work with BigQuery. We need to install separate package to work with Cloud Spanner, with Bigtable, and so on. And lastly, what about data orchestrators? Well, AWS has a service called Managed Workflow for Apache Airflow, so we don't have to manually install Airflow scheduler and workers. GCP did it even earlier, and they've got Cloud Composer, which is also an Apache Airflow. And Azure may not have any Python-based orchestrator, but we can easily set up Airflow or any other tool of our preference in Azure virtual machines. So, as you can see, all the biggest cloud players accommodate Python users in their solutions. And before we finish, let's take a look at some honorable mentions, which didn't reach the main core of the presentation. So firstly, we've got great expectations, and trust me, this could be another presentation. Great Expectations is a great tool for data testing, creating documentation for data and data profiling. We've got Gazpacho, which could be an alternative for Beautiful Soup. We've got Faust for processing Kafka streams in Python, the way that the Kafka streams are doing it. We've got NumPy for fast mathematical work with arrays. And by the way, Pandas, for example, is built on top of NumPy. We've got two of Apache Spark siblings, so Apache Flink for streaming and Apache Beam for building data pipelines. Now, it's worth mentioning Apache Beam because it is used by Google Cloud Platform in their service called Dataflow, right? The Apache Beam is included in Dataflow. We've got Matplotlib and Seaborn for statistical visualizations and graphics. And we've got PETL or PETL for simple ETL jobs. And that's all. Thank you for your time.
All right. Hi again, Max. Thank you so much for the presentation. Thanks everybody for attending, and we are open to questions, of which we don't have any just right now, so we're waiting for those to roll in. Remember, we've got a few minutes for Q&A, just a few minutes, and then we'll move on to the next presentation about domain-driven design by Sebastian Buczynski. He's just preparing his presentation right now. I can see it on my screen. It's coming up, but you can't yet. Anyway, waiting for those comments to roll in. Max, anything else to kind of add on top of? Oh, never mind. I was trying to come up with a question, but thankfully Bartosz is saving me here. Bartosz is asking, and thanks again, Bartosz. You're really active in the chat today. It's noticed and appreciated. He's asking, do you think tools that protect websites from being scraped should be a thing? I'm very curious about that. Yeah, what would you?
That's a really tricky question. Do you think that tools that protect websites from being scrapped should be a thing? I think that yes. A short answer would be yes. I mean, you should have an option to protect yourself, right? I've seen a lot of examples of, maybe not seen, but I've heard a lot of examples of companies that they were scrapping data from some other website just to gather data and later use it on somehow in their services. So I think that yes, you should be somehow able to do it. Those tools, are not designed with bad intention, right? Beautiful Soup is just to parse HTML files, not to scrap data directly. So you may want to just work with HTML files to prepare them for your own website, like I mentioned, you can replace some tags, so on and so forth. So, but yes, that's a very interesting question. That could be a topic for a separate discussion, I think.
Yeah, and I wonder how possible it would be to actually create tools like that. Sorry, I do have a bit of a personal stake in this to some extent, because My pet peeve is when there are these news stories about like LinkedIn got hacked, 90 million accounts data is out there, check if you got hacked. And it's not really hacking. They just got scraped and everybody's making like a big deal out of it. But ideally, I think it wouldn't be possible to get that sort of data from LinkedIn through scraping. So just, my 2 humble cents from the host.
Well, the sad issue about one of these libraries that I've presented, or maybe not the sad, but I do believe that they can even provide you the opportunity to log into the website that you are scrapping. So they went a step further, but don't quote me on that. Check it. To be honest, I haven't really used it in production. So
okay. All right, we've got one more question coming in from Jacek. Also not the first question from Jacek, not the first comment. Thank you for being active. This one is a two-parter. The first one is, how do you deal with scraping dynamically generated pages? And he goes on to elaborate, dynamically as in some JS framework generating them client-side. What would you say?
I'm really happy that with the previous question I said that I haven't used it in production, because I don't really know how to answer that question. I was rather working with data pipelines and data warehouses than scraping data from websites. So I'm sorry, Jacek Jaworski, if you can leave us with some email. I would like to go back to you with an answer maybe tomorrow or next week, if that satisfies you.
Okay, very interesting. No problem, Max, to jump into the chat later on when this finishes to continue the discussion. I can see there's actually people are answering Jacek's question with ideas already. So
right.
I'm not going to feature all of the comments again because the time does not allow for everything. But Jacek is saying fair enough. Thanks for the presentation. And Bartosz is saying thank you for the answer. Everybody's thankful. So I think that's a nice note to end on here, because we don't have any more questions rolling in, and we'll stay right on top of the agenda. It'll give us time for this switch over. I'm removing your presentation.
Okay,
I'm
thank
removing you. Thank you, Max, for the presentation.
Have a nice evening. See you later.